Hi Year 12, this is our third lesson for the topic of applications of differentiation. In this lesson we're going to look at curve sketching. Okay, we're halfway there. We have two very important applications coming up, however. This is what we've learned: sign of the first derivative and the first derivative test, turning points, inflections and horizontal inflections, the sign of the second derivative test and its limitations. Before we start, we had this question from last lesson. We have a 10 centimetre high glass that's been filled with water at a constant rate by volume. Let y equals f of t be the depth of water in the glass as a function of time t. Find the approximate depth y1 at which dy dt is a maximum. So as we're going up here, we can see this is being filled increasingly rapidly until we get to here when it starts to slow off. The rate starts to slow off. So this is a maximum here at y equals 2. And it slows off until it gets to here, and there's another change in concavity when it starts to speed up a bit. So this is a minimum here at y equals 7. Now we're asked to graph this. So what they're looking for, let's label these axes. We have time t, and we have a maximum depth of 10. Now we also know, let's put a scale on this axis, that the rate of change is increasing up until y is equal to 2 centimetres, and then it's slowing down up until y equals 7. We're not going to know the times when those two things happen, but that's all right. So we've got an increasing rate of change here, then it starts to slow down, and then it increases again until it's full. So this is T1 and T2. Now when we sketch a curve using calculus, we follow this method. Firstly, find the y-intercept and the x-intercepts if required. Differentiate and solve the first derivative equal to 0 to find stationary points. Differentiate again and solve the second derivative equal to 0 to find inflections. Use the second derivative or first derivative test to determine the nature of any stationary points. Are there any asymptotes? What happens as x approaches positive or negative infinity? Are there any specified endpoints? And finally, draw a half-page sketch and label all critical points. A critical point occurs either when the first derivative is equal to 0, which will result in a turning point. If the second derivative is less than 0, it's a maximum, greater than 0, it's a minimum, or a horizontal inflection, where the second derivative is equal to 0. Or a critical point is where the first derivative is undefined. And remember, that can happen when we've got a pointy bit in a graph or a discontinuous bit. So here's an example of a curve with various critical points. So here we have a local minimum, which is a stationary point, and here is a local maximum, which is also a stationary point. This is also a local minimum, but the first derivative is undefined because it's pointy. Then we have a horizontal inflection here, so first and second derivatives equal to 0. We have another local maximum where the derivative is undefined. And then we have a discontinuous part of the graph, which is here. And again, f dash of x is undefined. And this point up here is an inflection, but the first derivative is not equal to 0 there. Okay, let's look at our first example. Sketch the curve y equals x cubed, take away 12x, take away 1 for the domain -4 up to +4, showing all critical points and inflections. No need to find the x-intercepts. So we're going to start with the y-intercept because that's the easiest. We're going to substitute in x is equal to 0, 0, 0, -1. So the y-intercept is 0, -1. I'm going to highlight that because I'm going to show that on the graph. Now it says the x-intercepts are not required, so we'll leave those and we'll do the derivative. It is 3x squared take away 12. Right, we want to solve this equal to 0, and I need to factorise this. So I've taken the 3 out, got x squared take away 4. This is x plus 2, x minus 2. And now we have the null factor law. Either this is equal to 0 or this is equal to 0. So x is either 2 or -2. Now we need to find the corresponding y coordinates for those 2 points. So we need to substitute x equals positive 2 into here, and then substitute negative 2 into here. So at x equals 2, y is equal to 8 take away 24 take away 1, which is negative 17. And at x is equal to negative 2, we've got negative 2 all cubed, which is negative 8, take away 12 lots of negative 2, which is positive 24, take away 1, which is 15. Now we need to test those points, so we need the second derivative, which is 6x to the power of 1. At x is equal to 2, the second derivative, substitute this in, is equal to 12, which is greater than 0, therefore it's concave up, therefore there is a minimum at the point 2, negative 17. And let's highlight that. Now let's do it for negative 2. At x is equal to negative 2, we substitute it in here. It's equal to negative 12. Make sure you give this value, otherwise you will lose a mark. Which is less than 0, it is concave down, therefore it's a maximum at negative 2, 15, and highlight that. Alright, so we have got a y-intercept, and we have a minimum and a maximum point. The next thing we want to do is find any inflections. So we take our second derivative and we put it equal to 0 and solve. X is equal to 0. We need the y coordinate as well, so we're going to substitute this into here. We already did this actually because it is the y-intercept. And at x equals 0, y is equal to negative 1. So there's an inflection at 0, negative 1. Okay, we have one more thing that we need to do because this curve has no asymptotes, so we can skip that step. But it does have a restricted domain, so we need to know these endpoints. We know the x coordinates. To find the y coordinate, substitute it into the curve. So at x equals negative 4, y is equal to negative 64 plus 48 take away 1, which is negative 17. So the endpoint is negative 4, negative 17. And substituting in 4, we get 64 take 48 take 1, which is 15. And here's our other endpoint. Now when you're sketching, draw a large diagram, a third to a half a page. Make sure your scales are consistent. They don't have to be the same as each other, these ones aren't, but they have to be consistent within themselves. Label all your points, so here's a maximum, here's a minimum, here's an inflection, it's also the y-intercept, and here are the endpoints. And label your axes. Here's example 2. Sketch the curve y equals x to the power of 4 take away 2x cubed and show all important features. So we'll start with the y-intercept. Substituting in x equals 0, we get y equals 0. Can we factorize? Yes, we can. So we can find the x-intercepts. So x-intercepts occur when y equals 0, so substitute your 0 in here. I'm factorizing, I get x cubed multiplied by x minus 2. We have a null factor law, either x equals 0, which is actually this point, or x is equal to 2. And so the x-intercepts are 0, 0, and 2, 0. Now let's do the derivative. So y dashed is going to be 4x cubed take away 6x squared. And we want to solve that equal to 0. And we can factorize, which gives us 2x squared outside of 2x minus 3. So either x is equal to 0 or x is equal to 3 over 2. We need the y coordinates. When x is equal to 0, y is equal to 0. And then substituting in the 3 over 2, just use your calculator into here, we're going to get negative 27 on 16. So our stationary points are 0, 0 and 3 over 2, negative 27 on 16. Now we're going to test the nature of those stationary points, so we need the second derivative. We have 12x squared take away 12x. Now I'm going to start with x is equal to 3 over 2, and substituting that in, our second derivative is 9, which is greater than 0, therefore it's concave up, it's a minimum. So we have a minimum at this point. Now I'm actually going to write it to 1 decimal place, just so that it's easier to graph. Now let's do x equals 0 because the second derivative ends up being 0 as well. So this is a possible horizontal inflection. So remember that we need to now go to the first derivative test. Here's our first derivative. We have the point 0, 0. We want to test either side. So negative 1, 0, and 1. Substituting the negative 1 in, we get negative 4 take away 6 is negative 10. 0 will give us 0. Substituting the 1 in, we get 4 take away 6 is negative 2. So we've got negative, flat, negative. It actually is a horizontal inflection. And lastly, let's find any ordinary inflections by solving the second derivative equal to 0. Factorise, we have 12x outside of x minus 1. So either x is equal to 0, we already know about that one, or x is equal to 1. This is new information. So we're going to have an inflection at x equals 1. Substitute back into the curve to get the y coordinate, which gives us an inflection at 1, negative 1. Right, here's our graph. We have a horizontal inflection here at 0, 0, a normal inflection at 1, negative 1, and we have a minimum point at 1.5, negative 1.7. And then make sure that your ends of your graph go above the x-axis and put arrows on both sides. Example 3. Sketch the curve y equals x over x squared plus 4, showing turning points and asymptotes. So start, as always, finding the y-intercept. Substitute in x is equal to 0. Gives us 0 over 4, which is 0. Now if we go and try and find the x-intercept by substituting in y equals 0, we're going to end up with exactly the same point, x equals 0. So we can leave that. Now let's do the derivative. So this is a quotient rule. Our numerator, x, is going to be equal to u, and our denominator, x squared plus 4, is going to be equal to v. Do the derivatives. U dashed is equal to 1, v dashed is equal to 2x. Let's construct the quotient rule. We want v multiplied by u dashed, take away u multiplied by v dashed all over v squared. And tidying up the numerator, we end up with 4 take away x squared all over x squared plus 4 all squared. Now we want to solve this equal to 0. But here's the thing, we only need to solve the numerator equal to 0. The denominator can't equal 0, so we can actually ignore it. So we're going to solve 0 is equal to 4 take away x squared. Factorising this, we get 2 minus x, 2 plus x, which gives us x is equal to plus or minus 2. Now we need to substitute back into this to find our y coordinates. So when x is equal to 2, y is equal to 2 over 8 or 1 over 4. And when x is equal to negative 2, y is equal to negative 1 over 4. Now we need to test the nature of the turning points. Now we could do the second derivative, but it will be quite complicated. So I'm actually going to use the first derivative test. So we want to test either side of x is equal to negative 2 and either side of x is equal to 2. And just doing it quickly, substituting the numbers in, we get negative, 0, positive. So this one here is a minimum. This one, substituting in, you can check these later on, we get a maximum. Therefore, there's a minimum at negative 2, negative a quarter, and a maximum at 2 a quarter. Now, something we haven't had to do in our previous examples was find asymptotes. We've got to consider vertical and horizontal asymptotes. Now remember, vertical asymptotes are easier to find. All we have to do is solve the denominator is equal to 0. This actually has no solutions. This is x squared is equal to negative 4, can't do the square root of a negative number. Now, to find your horizontal asymptotes, possibly the best way is to take the limit as x approaches infinity of the function. And if you remember this from year 11, we are going to divide every single term by the highest power of x, which is x squared. Keep your limit notation. So x over x squared is 1 on x. X squared over x squared is 1, and then 4 over x squared. The limit as x approaches infinity of this is 0 over 1 plus 0. And 0 divided by 1 is 0. So there's a horizontal asymptote at y is equal to 0, which is actually the x-axis. Okay, we're ready to graph it. So we have our horizontal asymptote here on the x-axis, a maximum at 2, 1/4, a minimum at negative 2, negative a quarter. We can see our graph getting closer and closer on both sides to the asymptote. There is an inflection here which we didn't have to find, but you can put it in if you want to. Okay, that's been a fairly big lesson. Let's summarize what we've learned. It's really important that you know the difference between the curve, the first derivative and the second derivative, and their respective purposes. So let's go through them. The curve. The purpose is to find the y-coordinates of any points. So anytime you find a critical point, like a turning point, go straight back into the curve to find the corresponding y-coordinate. Remember, y-intercept occurs when x is 0, x-intercepts occur when y equals 0. The first derivative. The purpose is to find any stationary points. If the first derivative is greater than 0, the curve is increasing, less than 0, it's decreasing, equal to 0, it's a stationary point. We can use the first derivative test to test the nature of any stationary points. Second derivative. The purpose is to test concavity or change in concavity. Remember, if the second derivative is greater than 0, it's concave up, it's a minimum. Less than 0, it's concave down, it's a maximum. Equal to 0, it's an inflection. If first and second derivatives are both equal to 0, there's a possible horizontal inflection. We need to go back to the first derivative test to confirm it. And here's my Year 12's top tips. Don't forget to label your minimum, maximum and inflection point. Label your x, y axis, minimum point, maximum point inflections. Remember how to find inflections. Remember to add the arrows on both ends of the graph. Find the y-coordinates by substituting the x values into the original equation. If the second derivative is greater than 0, it's a minimum. If it's less than 0, it's a maximum. Use a ruler. It's better to overdo a graph than underdo it. Just list everything on the line. Don't forget to point out asymptotes when they are the same as the x or y axis. Remember to point out the coordinates of the endpoints and the point of inflection. And to finish off, here's a couple of past HSC questions that you can do. The first one's from 2020, question 16. Sketch the graph of the curve y equals negative x cubed plus 3x squared, take away 1, labelling the stationary points and point of inflection. Do not determine the x-intercepts of the curve. And the second one's from 2021, question 19. Without using calculus, sketch the graph of y equals 2 plus 1 on x plus 4, showing the asymptotes and the x and y intercepts. Okay, that's it. We have one more lesson to go on this topic, and it is on optimization.